Hey you guys, here's a second installment of chapter 4. Like I said, chapter 4 is pretty long. We're still in aqueous solutions. Aqueous solutions mean solutions in a water base. I was just looking at your textbook and I said this was a wastewater treatment plant, and that is not it. Apparently it's putting ocean water in large evaporation beds, and then you can mine magnesium from the ocean, but it's basically you get magnesium chloride, and then you can convert it into magnesium metal through electrolysis, but which is putting electricity into there. But either way, anyway, this was not a wastewater treatment plant. Looks similar. Now let's talk about acids. We're starting on acid and base section. We already learned how to name acids in chapter 2, but let's talk about their properties. They have a sour taste. Vinegar is acetic acid, and citrus fruits are citric acid. And what acids do is cause a color change in certain plant dyes, like that red cabbage or even radishes. The red on radishes is an acid-base indicator. They react with certain metals and produce hydrogen gas, such as magnesium. And this was something we saw previously. Magnesium reacting with hydrochloric acid makes hydrogen gas. They react with carbonates and bicarbonates to produce carbon dioxide gas. So here you see the bubbles of, well, actually this is hydrogen. I can see the piece of metal right there. But baking soda and vinegar will give you carbon dioxide gas. Here's a calcium carbonate like limestone. Here's limestone reacting with hydrochloric acid, and it basically eats it away and makes carbon dioxide and water. Aqueous acid solutions conduct electricity because they are ionized. Bases, on the other hand, have a bitter taste. They feel slippery because soaps are bases also, and they can also cause those color changes. Aqueous solutions of base conduct electricity because they're ionized. And here's some examples of a basic solution. Ammonia will create a basic solution because it will react with water. And when it reacts with water, it's a base, so that lone electron pair here, now this is out of later chapters, but I'm kind of giving you a heads up, it steals a hydrogen and it makes ammonium and hydroxide. So when you go buy an ammonia solution from the grocery store for a cleaning solution, it's actually this, because this is the aqueous part. But aqueous, there you go. But when you open the lid, you will smell ammonia gas, and that's because this is reversible. Now, there's different definitions of acids. An Arrhenius acid is one that produces hydronium ions in water. An Arrhenius base is one that produces hydroxide ions in water. And this is the same formula or equation that I just wrote for you on the previous slide. And there is the H3O plus being produced by an acid through its reaction with water. A Bronsted acid is a proton donor, and a Bronsted base is a proton acceptor. So when we look at those previous equations, we kind of see some overlap. This is a Bronsted base because it accepts a hydrogen from water, and water is acting as the Bronsted acid. So there's your base and acid and base, and these are called conjugate acid-base pairs. So in the forward direction, ammonia is the acid, but in the reverse direction, I'm sorry, I messed that up. In the forward direction, ammonia is the base, but in the reverse direction, ammonium is the acid. A Bronsted acid must contain at least one ionizable proton, and this proton is also meaning a hydrogen. So monoprotic acids are acids in which it has one hydrogen to donate, and you'll notice the one hydrogen here and here. And these are all strong acids, but this one's a weak. Notice the reversible arrow. Diprotic acids have two to donate. This guy is strong. The first one is anyway. The second one is weak. Triprotic have three. Here's three acids, but this is actually weak. You can notice by here that this is phosphoric acid is a weak acid. And there's the second step of the ionization of phosphoric acid. And do we have the third? We have the third step. So this is a triprotic acid and is able to donate 3 hydrogens. Here are some common strong and weak acids. So we just saw a lot of these on the previous slide. Weak acid is hydrofluoric and nitrous, and phosphoric and acetic. So when you write their reaction of all of these with water, you would put in a reversible arrow. whereas all these would be a direct arrow. It went in their reaction with water plus H2O. Okay, so when we identify them as a Bronsted acid, base, or both, you look at whether or not it can donate a hydrogen, and that hydrogen must be ionizable. So that means it has to be attached to an electronegative atom. Like these hydrogens right now on this acetate anion that I'm pointing to here are attached to carbon. So they are not ionizable because they have to be attached to an electronegative atom. Now it's hard to tell that. I mean, and so you'd end up having to do some research and memorization. So hydroiodic acid is a strong acid, and it's a Bronsted acid. Acetate, notice what it's doing. It's actually reacting like this. That's H3O plus to make acetic acid, so it is a base. It's a proton, our hydrogen acceptor. So it had its electrons out here, and you went out and grabbed one of those hydrogens. This is hydrogen dihydrogen phosphate, and dihydrogen phosphate can do either one, I would think. It'd be a Bronsted acid, the way it is being shown, or it could be a Bronsted base. So it can donate, this is a little bit misleading, it can donate a hydrogen to water. See, so this guy went out and took a hydrogen, so this was acting as an acid. Or this, if this is now H3O, this guy went out and took a hydrogen from here, which makes it a base. So it can do both. This guy only has a hydrogen to give. He can't pick up any more hydrogen, so he has to be acting as an acid. This NO2 minus doesn't have any hydrogens to give, so it must be acting as a base. And you'll notice what he did. He went out there and picked up a hydrogen. Again, this is H3O. So as far as neutralization, we have talked about acids and bases. A neutralization reaction is a reaction between an acid and a base to make salt and water. So here's hydrochloric acid reacting with sodium hydroxide. And if you do the switch, here's positive, hydrogen is positive, chloride's negative, positive and negative hydroxide. Remember, hydroxide is negative as a whole. So the hydrogen is going to go with the hydroxide and make water. Remember, water can be written as HOH. So the H went with the OH. And salt, this is the salt, this is table salt, but positive goes with negative. That's a neutralization reaction. This is the complete ionic equation, and then there's a net ionic equation once we take away our spectators. So in a neutralization reaction, this is the commonality between all of them. Heat is produced and water is produced in a neutralization reaction. The salt can be many different salts, but this is the mainstay. So a neutralization reaction that involves a weak electrolyte, it's a little bit different. A weak is still acid plus base to make salt and water. It looks just slightly different. Let's check it out. There's hydrocyanic acid, sodium hydroxide, to make sodium cyanide and water. So you got your salt and water. So it looks like we canceled out sodium as the spectator. But what it looks like here is that we still have this left in solution. So there's a little bit more. As far as the strong acid and base, we had just creation of water from hydrogen and hydroxide. Here there's a little bit left of those other things, because since this is a weak electrolyte, you're going to have a little bit of this left. Acetate does the same thing. So acetic acid, this acetate reacts with water. You might have some of the acetic acid left in solution. Acetic acid is a weak electrolyte, and it smells like vinegar. So you would still have, this is what smells like vinegar. So you would still have some of this left over in solution. So a neutralization reaction that produces a gas, you can still have acid base plus to make salt, water. And now I have carbon dioxide here. Now in order for carbon dioxide to be created, looks like we would need a carbonate. And here's a carbonate that is going to react with hydrochloric acid to make carbon dioxide, water, and sodium chloride. So when the kind of the intermediate step of this is to make what's called carbonic acid, and carbonic acid then decomposes into these two pieces. So sodium goes with chloride, hydrogen goes with carbonate to make carbonic acid, which decomposes into carbon dioxide and water. Looks like I'm showing you here the complete ionic equation, and the net ionic equation. So there's your net ionic equation to make the carbonic acid, which then goes to carbon dioxide and water. There are some other acid-base reactions that can make gases, and one of them is if you have a sulfite in there instead of carbonate, you can make sulfur dioxide gas. If you have a sulfide and you have hydrogen, you can make hydrogen sulfide gas, and this really stinks. We do make this in one of our labs, and it's actually pretty toxic if you have too much of it. So we can create this, say for example, we were going to mix hydrochloric acid plus sodium sulfide, and I think this is one of the ones that you do in your lab. The sodium goes with the chlorine, and you end up with sodium chloride, and then the hydrogen goes with the sulfur to make that hydrogen sulfide gas. That stinks. It's still an acid-base reaction, but it doesn't make salt and water. It makes salt and hydrogen sulfide. So let's do an example of hydrobromic acid and barium hydroxide. First, of course, you need to write all your chemical reaction here and make sure it's balanced. Hydrobromic acid and barium hydroxide. The barium goes with the bromine, and the H goes with the OH to make water. So when you write your complete ionic equation, you'll see your spectators cancel out. The spectators were the barium, and the bromide, and then you have hydrogen hydroxide to make water left over. And that's your net ionic equation for any neutralization reaction. Now you'll notice that in this example there were 2's and 2's, but when you narrow it down to the most simple form, it's a 1 and a 1 and a 1. Now let's change gears a little bit. Now the acid-base reactions we just did, we're now going to look at oxidation reactions, oxidation reduction reactions. But before we do that, we want to learn what oxidation number is, because oxidation number by definition is what a change in oxidation number is what makes something a redox reaction. So as far as the oxidation number for an atom in a molecule or a formula unit, the charge that atom would have, that's what oxidation number is if the electrons were completely transferred. Now that's not always the case. As far as complete transfer, we would think about ionic compounds. But there are covalent compounds, but we can still treat this the same. We can still treat it the same. It's like a bookkeeping method for understanding how electrons are being exchanged. So oxidation number for free elements is always 0. So I started out with this in the beginning of the semester, and I would list something like sodium, and if it was just straight sodium metal, I would put a 0 with it. So all of these, if it's just listed by itself, these have a 0 oxidation number. They're elemental. No electrons have been exchanged. If it's a monoatomic ion, the oxidation number is the charge on the ion. So if lithium plus is listed for you, the oxidation number on lithium is +1. If it's listed as Fe3+, the oxidation number on iron is +3, and so on. Oxide is O2 negative, so the oxidation number on oxygen in oxide is O -2. Now, sometimes we have to know there's different options for oxidation number for different elements. Now, the oxidation number of oxygen is usually -2, 9 times out of 10. So if you saw Li2O, like lithium oxide, the oxidation number here is -2. But if I would give you something like Li2O2, that looks a little bit different, and that is a peroxide. So peroxide is O2 2-, and its oxidation number is -1. And that's because there's 2 oxygens stuck together, and when they're stuck together, each one of them has a -1 charge, so it's listed as O2 2-, and it goes as a group like that. So if I put lithium with that, I would need lithium on one side and a lithium on the other side to balance it out, because each lithium is +1. The oxidation number of hydrogen is +1 unless it's with a metal and it's -1. Group 1A metals are +1, 2A +2, and fluorine is always -1. And the sum of the oxidation numbers of all the atoms in a molecular ion is equal to the charge on the molecular ion. And sometimes you actually get fractions. So this guy is called a superoxide. And superoxide is at O2 with a negative charge. So if I put superoxide together and made a compound with lithium, I put it together like this, the formula is going, since there's +1 and -1, the formula would look like that. That's lithium superoxide. If you remember on the previous slide, I also showed you lithium oxide, Li2O, and then I also showed you lithium peroxide, which would be Li2O2. So you see, oxygen can do all these things, but it's going to be reflected in the formula of the compound. So let's do a practice here. What are the oxidation numbers of all the elements in bicarbonate? So HCO3 just showed up there. Oxygen likes to be -2 almost all the time. Hydrogen likes to be +1 almost all the time. Now what we want to solve for is carbon, because carbon can have some variability. So if we then think about it this way, that there are 3 oxygens and they're all -2. There's 1 hydrogen and it's +1. And the whole thing must equal -1 because bicarbonate is negative. Just plug it in like an algebraic equation, and you get that carbon has an oxidation number of +4 in bicarbonate or hydrogen carbonate. So what does an oxidation reaction mean anyway? It's an electron transfer, and that electron transfer is tracked by that change in oxidation number that we were just learning how to assign. So in an example here, we have a burning of magnesium metal. When magnesium metal burns, it combines with oxygen gas to make magnesium oxide. And this is the ash that you would see left over. So when that happens, magnesium gets transferred to, is altered to magnesium 2+, oxygen is altered to O2-. This is called an oxidation when something loses electrons and becomes more positive. This is called a reduction when something gains electrons and becomes more negative. So when I say becomes more negative, it goes from O0 to -2, that's more negative. And then magnesium from 0 to more positive, that's an oxidation. And then if you add these 2 reactions up, you'll see 4 reactions were lost, but 4 reactions were gained, and then those cancel out. And the overall reaction looks like that. So this is an oxidation number of 0, 0, +2, -2. So magnesium was oxidized and oxygen was reduced. So here's an example out of your textbook. This is a figure that shows copper. It looks like copper is being put down in a silver nitrate solution. So this was silver nitrate, and the copper metal was put down in there. And then you see what is showing down here in the schematic is that copper goes into solution, silver comes out of solution. Now, when I say comes in and goes out or whatever, copper was Cu0 going to Cu2+ in solution. That's an oxidation. Silver was a cation, and now it's going into the metallic form on the surface. So all of this silver solid you're seeing growing on this is like, they're like crystals of silver metal. That's a redox reaction. Now, is this a redox reaction? If I put zinc down in a copper sulfate solution, what would I see? I would see zinc going into solution from zinc metal to zinc 2+, and I would see copper coming out of solution, copper 2+ to copper 0. So I would see copper metal grow on the surface of the zinc. Zinc being oxidized, and zinc is now called the reducing agent. The reducing agent is the element that gives electrons to somebody else. So zinc metal gave electrons to copper 2+ and reduced copper 2+ to copper metal. Copper 2+ is being reduced by zinc metal, and copper 2+ is the oxidizing agent because it took electrons from zinc metal. So when we look at this type of reaction, this was on the previous slide, this copper wire reacting with silver nitrate to form silver metal. What is the oxidizing agent? If it goes from 0 to plus, this is where we have to practice assigning these numbers. Silver is +1. Now, this is a little tricky. Nitrate as a whole is -1. But if we break it down, and we would find that nitrogen is +5, oxygen is -2. But you'll notice it's still nitrate over here. So this whole thing is -1. This is still +5, and that's still -2. So you try to figure that out by doing those little algebraic equations, but you see that nitrate is a spectator at this point. Copper is oxidized, silver is reduced down to 0. And there's the half reactions. So as far as just practicing what are oxidation numbers, if we look at sodium iodate, sodium is +1, oxygen is -2, and then we just plug it in for iodine and find iodine to be +5. IF7, F likes to be -1, remember, all the time, so then F iodine must be +7. And in potassium dichromate, potassium likes to be +1 and oxygen likes to be -2 most of the time. So then you solve for chromium and find chromium to be +6. And chromium 6 is a common oxidation state for chromium. So this is kind of the larger periodic table that I was talking about in chapter 2, that this shows all the possible oxidation numbers for the elements on the periodic table. And so if we look at what chromium that we were just looking at in Na2Cr2O7, chromium is right here, and we just solve for chromium 6. And chromium 6 is a common oxidation state. From a previous PowerPoint slide video that I did, we talked about chromic and chromous, chromium 3 and chromium 2. That's the ick and the us of those two guys. But you see, chromium can do lots of different things. So this is like a little reference chart. Reference this chart in order to determine if your oxidation number that you calculated, first one does exist, and secondly, is it most common? And if you're trying to figure it out, you can just use this to figure things out. So let's talk about types of oxidation reduction reactions. There's a combination reaction. A combination reaction is something where two things come together to make one. So we have aluminum here plus bromine to make aluminum bromide, and that's a combination reaction. So there's your oxidation numbers. So that's a redox reaction, aluminum being oxidized and bromine being reduced. If we were going to do the half reactions here, we would see aluminum metal being converted to aluminum 3+ plus 3 electrons. That's the half reaction. Now, since there are two of them here, you see a 2 here and a 2 here, that translates this into 6. So when you add them together, your 6 electrons will cancel out. For our decomposition reaction, it's kind of the reverse of a combination reaction. And this is also a redox reaction. Potassium is +1 here, +1 here. That doesn't change. Oxygen is -2. This is 0. So that's oxidized. So this guy must be reduced. And to figure that out, here's a -1, +1, -1. This guy's probably one of those positives. Now to figure out which one it is, you would put -2 times 3 is -6, and a +1. This guy must be +5. And sure enough, that is a reduction. And there's the numbers, but I already wrote them over for you. Okay, how about a combustion reaction? Is that a redox reaction? Yes, it is. Now this one I like to put the 8 here because that Beck's me. I think it should be 8. I think it should be 8. But either way, when you burn sulfur, it goes from 0 to +4, and this guy goes from 0 to -2. So you see oxygen is reduced and sulfur is oxidized in this case. And in this case, it is another redox reaction, magnesium being oxidized, if you look at the numbers, and oxygen being reduced. Displacement reaction is one in which one element displaces another. So it looks like element A came and kicked out element B and then combined with C. So B was kicked out. Strontium in this example, this is a displacement reaction, but it's called a hydrogen displacement reaction. And you can see the change in the numbers. And when you have the change in the numbers, strontium was oxidized, hydrogen was reduced. Here's another displacement reaction, but it's called a metal displacement reaction. Magnesium displaces the metal titanium. If you look at the numbers, titanium goes from +4 to 0, and magnesium goes from 0 to +2. Chlorine looks like the spectator ion. Here's another type of displacement reaction, but it's a halogen displacement. So one halogen, this is column 7A, displaces another. You look at your oxidation numbers, chlorine went from 0 to -1, and bromide went from -1 to 0. So this would be a reduction, and this would be an oxidation. Now the activity series, this is a way of, after chemists studied the planet, for a while and studied all these different elements and said, oh, it looks like this is the pattern. That lithium really likes to be oxidized. Gold really likes to be reduced. Lithium likes to be on this side of the reaction. Gold likes to be over here. And that's why gold metal lasts forever. It's just going to be at the bottom of the ocean. So any element on the left will replace any ion on the right. Now, when we say replace, I feel like we need an example here. So here is a hydrogen displacement reaction. M is a metal. Well, I mean, I guess you could look at hydrogen displacement. M replaces B. Now, any element on the left, so we'll replace any ion on the right. So let's say for my lithium and gold example, say I did lithium, had lithium metal, and I reacted it with gold. Now gold 3+, now gold is a common oxidation site, or gold 1+, nitrate. Lithium will kick out gold, and lithium is now combined with nitrate, and gold is on its own. And it's a metal. It's metallic. So now gold, lithium was on the left, and it kicked out or replaced an ion on the right. So lithium metal plus gold 3+, well, I did gold 1+, but that's not on here. And then it would go back and make gold metal and lithium ions. So in this example, where calcium react with water? Well, we can find water on this activity chart, or hydrogen. And it says calcium here. Now notice there are some things that are so reactive they react with cold water. Then some are not as reactive, so you have to heat the water to get them to react. Now the next grouping here does not react with water at all, but it has to react with an acid. And then this does not react with any of those things, this bottom portion. So copper, silver, gold, those are coinage metals, and they don't react too much with water. Now they can react with other things over time, like copper. A roof made of copper will react with carbon dioxide in the air to make a patina, which is called copper carbonate. It's green. So that's why your copper roofs look green. But what is calcium going to do here? Calcium, it looks like, is going to react. Where is calcium? It's right here. It reacts with water to produce hydrogen gas. Lead does not. And if you notice where lead is on this little activity series, it is below, it just does not react with water. So for halogens, though, halogens have their own activity series, fluorine being the most reactive, iodine being the least. So as far as what this activity series is, fluorine will always kick out another halogen and take its place, whereas iodine will not. Now, will chlorine kick out bromine? Yes, because chlorine is more active than bromine is, meaning that chlorine would rather be in chemical combination than bromine will. So that's kind of cool looking. This is how bromine is made. And there's your oxidation numbers showing the redox attribute. So will iodine kick out bromine? I don't think so. No, it won't, because iodine is not as active as bromine. One more type of reaction is called a disproportionation reaction, where the same element is simultaneously oxidized and reduced. Now, it's not the same atom of the same element, but it's the same element in the chemical reaction. So, for example, chlorine plus hydroxide makes hypochlorite, chloride, and water. So this is hypochlorite, chloride, and water. So if you look at the oxidation numbers, a chlorine atom gets oxidized and a chlorine atom gets reduced. That's what that means, but they're not the same atom. So there's an oxidation and there's a reduction. Okay, now as far as the classification, so when we look at these types of reactions, we might classify this as a precipitation reaction because a solid is formed. We might classify this as an acid-base reaction because it's an acid plus a base to make water and a salt. Now there is a salt somewhere, and this is kind of misleading because you might think, well, this is a hydrochloric acid solution, so your counterion would be Cl-. So here would be your salt, and there would be water. This would be a redox hydrogen displacement reaction. This would be a combination reaction, and they also be redox. So how can we continue on with this? Let's just do another example. Assign oxidation numbers, and you can classify the redox reaction and do that change in oxidation numbers. So it looks like this is a redox reaction. We have a reduction, we have an oxidation, and it's probably a combination. Oh, decomposition. Oh, look at that, I flipped it on my mind. Yes, this is a decomposition reaction. Here's a combination reaction. And the lithium is oxidized and nitrogen is reduced. This looks like a precipitation. No, it doesn't. The solid did show up, but it looks like a metal displacement reaction where nickel kicks out lead. And it is a redox reaction. And look at all the redox numbers. Nickel is oxidized, lead is reduced. And this one looks like, let's put our numbers on here, nitrogen went from +4 to +3, and nitrogen went from +4 to +5. Hydrogen did not change, and oxygen did not change. So we have nitrogen being both oxidized and reduced. Disproportionation. So this final slide was about a chemistry in action here, about a breathalyzer. And I don't know if this is the same breathalyzer that they use anymore. There's all fancy breathalyzers now that have the ability just to test the air. I mean, you don't even have to breathe into it. It's pretty cool. But this is ethanol that is being drunk in an alcoholic beverage. And then what they used to do is they would have the person breathe into it, and then it would go through basically a chemical solution, and then there would be a color change. And that color change, the more the green it got, the more ethanol was in the person's breath. And there's your color change. And it was detected with a meter, the cell of the photocell detector, which then showed up on the meter. So that's all for this part of chapter 4. This part of chapter 4 was about more solution chemistry, but we did acid base and we did redox. So go through this. Was a chemistry in action that told you how we use this in real life. That concludes this portion of chapter 4.